What I'd like to do today is to share with you the value of collecting the right sort of data as early as possible in the life cycle of your project, and the value of that throughout the life cycle. The explorationists amongst you would be familiar with the problem of getting the budget to collect decent multi-element geochemistry or spectral mineralogy very early in a project stage. So the thread through this talk is the value of the right data at the right time, and how it impacts the entire project life cycle. So when I'm talking about risk, in this instance I'm just talking about technical risk. And it's all about minimising the time, the cost and the uncertainty while maximising the expected value throughout the project value chain, but particularly at each decision point. So you've got the right information at the right time to make the right decision. And it's based on something quantitative rather than the gut feel of a geologist, no matter how experienced they may be. Part of this graph you guys will be familiar with. The blue bars are the perception of what it costs at each stage of the mine life cycle. The early generative stage, the general consensus is that it's a fairly low cost. So the left-hand y-axis there is a log scale of the expected expenditure. But what people forget is that at the generative stage, you've probably got to look at 500 projects to pick one, to have the likelihood or the chance of picking one that might be a winner. Okay, you step on then to the exploration stage, and you may have to look at 250 targets or projects before you get to the stage where you might pick one that eventually becomes a mine. So when you think of the cumulative cost at that early stage of doing that generative and exploration work, it's actually very, very high for each project that makes it to becoming a mine. The red line there reflects the y-axis on the right-hand side, which is the probability of progression to the next stage. A lot of the generative work that is done, projects are pushed into exploration when they probably should never have gone there because the data wasn't available to make an informed decision. The geologist didn't know whether there was a good chance of there being something of value on that project or not. So we'll pick up the project and we'll do our first phase exploration, and we'll spend quite a bit of money to prove there isn't something there. So the aim really in these instances should be, and the message to take home from this is, spend more on your generative stage, get some quantitative data, reduce the number of projects that you progress to exploration and save your money that way. Progress higher quality projects so that that black desired probability line is always on the uptrend, rather than putting a lot of projects through from generative to exploration and then failing to progress a lot from exploration because you've got a lot of junk in there that you've spent money on. So you can call this geometallurgy as a talk, you can call it integrated mineral systems analysis. It really doesn't matter. It's about quantitatively defining what your mineral system looks like in 3D as early as possible. There's a list of inputs there you can read for yourself, but you've heard people talk about the value of good quality logging that is focused on the mineral system style that you're looking for. The value of good, in this case, total digest ICP-MS geochemistry, broad sweep multi-element geochemistry, spectral mineralogy, geophysics, the petrophysics that goes with the geophysics so you can actually understand the geophysics and what the signature is telling you. All the way through to modelling the data as early as possible in 3D so you start to think about what your mineral system looks like. The applications are all the way from ground selection right through to mine closure. Okay? And the impact of doing this properly is that you have a cradle-to-grave unifying link across the mining value cycle. Okay? You get good provision of the critical knowledge early in the life cycle so you can make informed decisions earlier. And you get early warning of any fatal flaws and opportunities associated with projects, and you can make those informed decisions. So what's the value proposition? The costs are relatively small. At the very early stage, typically companies spend a very small amount of money on their project generation and selection. That's where you need to spend quite a bit more. Get out there and collect some representative samples at the point where you're looking at a project and define it quantitatively earlier on. But as you progress through, the percentage of the total project cost associated with collecting these data and doing something decent with them drops dramatically to the point where it's insignificant at the feasibility stage. If you're collecting the data earlier, then all of these steps are better informed. If you leave it to the last minute and you get to feasibility and say, haven't got enough quantitative data here, then it becomes a costly process, both time and money. So let's take step one, either the project acquisition or early exploration stage. If you are simply going out and collecting gold plus base metals when you're looking for a VMS system, as this case may be, and you use a relatively low-level technique or you don't select the right elements, then you may completely miss a signature that's present in the residual that points to a target undercover. Okay, I'm preaching to the converted. You guys know this, but it's amazing how many companies out there still don't collect these data early on because early stage, too expensive. If you step onto the advanced exploration stage, simply looking at a total digest ICP-MS method as opposed to ICP-AES, order of magnitude difference in the detection limits, in this case, you miss 2 blind porphyries and you don't even detect the outcropping one. Okay? So having the right method for the target you're looking for, and if you don't know what the target is you're looking for, then the broader spectrum method is ideal. I'll give a couple of case studies here. The first one for early implementation. This is where the right data, or at least a subset of the right data, was collected very early on in the project. I was exploration manager for Hot Chili at Productora, which is a Chilean coastal range, originally before I joined uranium project. But they were collecting ICP-AES data. It was rapidly recognised that this was a good copper-gold moly project, and it was thought to be a typical Chilean coastal range IOCG system. As we worked through the data, we started to see the porphyry signature and thought, maybe our copper-gold moly tourmaline breccias aren't IOCG related after all. Maybe they are a porphyry signal. So over the life of the project, collecting the right data sets, and the chemistry was just one of them, good logging, bit of spectral mineralogy was the other, we were able to start building three-dimensional models of the alteration geochemistry and the mineralogy. This is calculated mineralogy from geochemistry on just about every sample through the deposit. And we were able to start to map out, I'll show up here, the solid colours are alteration. So the red is potassic, in this case K-spar, not biotite, into cerussitic dominant in yellow, out to cerussite albite in green, and then albitic and sodic calcic in blues and purples. You can see up here the question mark. We had a zone we hadn't drilled through, but the MD was convinced there was nothing there. But the model was telling us something different. The copper grades here in the line work were showing that they're associated with the potassic alteration and that there was a gap in the drilling. So we went back and re-entered 2 holes that previously had been terminated about here, and you can read for yourself the results of having the right data that drove you to rethink your model, that drove you to re-enter holes and come up with intersections that most companies would be quite happy with, particularly below what was then the design pit shell, which was a preliminary design. So at the resource definition drilling stage, you do not want to miss the opportunity provided by good data and good interpretation, quantitative interpretation of those data to reduce your costs, or you can read the rest for yourself, okay? But at this stage, the total project cost, it's well below 1% of the total project cost to collect these data, so why would you not be doing it? Same project, now we're further north, now we're at feasibility stage. This project was always, not marginal, but it was tight in terms of tonnes and grade. And at the northern end, we knew from our geological model, we've been drilling this, that we've got fine breccia feeders blowing out into a potassic zone. So what we're looking for is these feeders coming up from beneath and then a nice zone of grade blowout. Except down here we had no feeders and we had one unexplained high-grade interval up in here. When we looked at the 3D model of the alteration from the calculated mineralogy and the mineralisation and so forth, what we saw up here was that this just was completely unexplained and there's something else going on. So we chased that, and the net result was not all of the system dips towards the west, and it's not all a perched high-grade breccia zone. This was a game changer. This basically increased the first reserve by 10%. Well, actually helped us build the first reserve, and contributed to more than doubling the resources in the system. So, at the feasibility study stage, this is where people start to think, now we really need a good geological model. Well, you're too late. You should have had it a long way before this. And if you've been collecting the right data, you would have had it a long way before this. And if you had those data, then the time to go through that feasibility process, get the metallurgists on board, get the engineers on board, get your block model filled with the sort of data that can contribute to optimising your feasibility study, optimising your mining studies, optimising your met test work, would all have already been done. Okay? So at Productora, it was already done. We had data on every 2 metre interval through the deposit. We were able to map out, so this is an east-west slice through that model that I showed you earlier, 3D model, the red potassic zones, the yellow sericitic zones, these advanced argillic sort of silica clay zones in waste. And from the geochemistry, from the calculated mineralogy and from the model, we're able to say something about what the properties, the rock properties associated with each of these domains are and how we should sample them for the metallurgical test work, and how much material belongs in each of those domains and how the grade relates to the different mineralogy types. So here with the potassic breccia zones, we can see that it is the majority of the ROM ore. The hardness is variable. Where there's case bar cement, it's as dense as anything, it's really hard. But where the tourmaline breccias exist, it's quite soft, friable and highly abrasive. So all this is really important in terms of understanding the costs associated with processing. The rest you can read for yourself. I'm going to skip on to zone 2. That was the second zone I showed you that was dipping back the other way. In this instance, it's called the Habanero zone, but what you need to know is it's hosted in this sericite rich ore. So it's higher grade copper. It had a locally very high pyrite content, so there's issues with potentially acid mine drainage. It was softer. So the bond work index is lower. It's going to cost less in the comminution. And we could say something about the percentage of sericite and clays and other issues from a processing perspective. So going through the geological model and the mineralogical model, even before you've done any met test work, you can say things that directly impact the design of met test work programs and mean that you select samples from the right domains. Up in the hanging wall here, there's very little mineralisation at all in this, but it has really dramatic effects on a pit high wall. This slope doesn't look like much, but believe me, it's hands and feet dragging yourself up a hill, typical Chilean Atacama geography. And so that becomes a real issue for the high wall. So that was a project where we had the correct or the best data, or at least enough of the best data to be able to make informed decisions quantitatively. What about if the horse is bolted? What about if you've got a project, you're at the feasibility stage, all you've ever collected is 5 elements, gold plus base metals, and you want to understand the metallurgy and how to sample for geometallurgy or for any of the other mining studies that you may need to do. The horse really has bolted. You can go back and collect these data, and for a lot of projects that we've worked on for clients, we've had to do that. And this is an example of a project that is in feasibility stage. It is marginal, it is big tonnage, and it's a complex skarn system. I can't say where it is or what the project is, but it's a tin, fluorite, copper, tungsten skarn, where 20% of the value sits in the fluorite as an industrial mineral, acid-grade fluorite. They're at the point where they really needed to get a geometallurgical model that could inform the met testing and help get the project across the line. One of the key things was they didn't have a resource model for the fluorite because fluorine was present in more than one fluorine-bearing mineral. The other problem was that whilst the logging had been done very, very carefully by very good observational geologists, what had been logged and the geological model that you can see in the top here, that the company had before we even joined the project, with a granite on the eastern side, the host rocks on the west, was extremely complex, virtually unminable, and didn't relate to the metallurgical properties, if you like, or even the mineralogy of the rocks. It was just the geologist's best guess, and they did their best to identify the lithologies. If we go back and take the 4-acid total digest ICP-MS geochemistry, we can define lithogeochemically, in a quantitative way, the key different rock types. Much, much simpler. Some mafic dikes running up through here, the granite on the east, a magnesium dolomitic sedimentary sequence, and then a calcareous sedimentary sequence. These two rock types were probably originally similar, and this has just been dolomitized due to its proximity to the granite and the fluids associated with that. So immediately, having these extra data, you can simplify your models down to what really matters in a lithological sense. But this still didn't answer the question about what is the current mineralogy for this project. Taking that same ICP-MS data, combining it with some spectral mineralogy and a few other techniques, we were able to then build a fairly complex calculated mineralogy model. Okay? By fairly complex, I mean, we start off splitting it down to what we think the mineral assemblages are, and we look at the relationship of those. In this instance, you've got topaz, a magnetite skarn, this is fairly intense alteration here, and the K-feldspar in the proximal zone around the tin mineralisation, which is predominantly cassiterite, but not all cassiterite. And then out into more chloritic sequences in green, and into problematic clays and smectites in greys and blues. Any metallurgist in the room is immediately rolling their eyes at the smectite going, "Gee, we need to know where that is." But we can simplify that back to the alteration mineralogy, take away the weathering effect, take away the precursor protolith lithologies, and just look at the alteration. And it can be simplified down, in this instance, to a dominantly quartz topaz zone in blue, the magnetite skarn in purple, and effectively calc silicates everywhere else in yellow. And these have distinct mineralogy, distinct processing characteristics. Some of the issues, for instance, with the magnetite skarn is we're going to try and get a gravity separation of cassiterite, but the density between the cassiterite and the magnetite is similar, and the magnetite's ultra-fine grained. And so there's an issue there with optimising the gravity separation. The quartz topaz zone in blue, super high grade, but really hard and abrasive. Right? So again, we can go through this process even before the MET test work has started and say, this is what we expect from these domains. Let's specifically select composite samples from each of those domains, knowing what we know from the model, so that we can get a truly representative set of samples for variability test work for each domain, rather than the metallurgist saying, I've got 6 holes. Where do I drill them? How am I going to get a representative sample from 6 holes into this deposit? So we can take those data points that are mapped to the drill holes based on quantitative data for each interval. In that case, it was just one sample every 5 metres down the hole. Okay, so it wasn't a complete resampling of the entire system. And we can build live 3D models. These are not the most precise models you'll see, but for GEOmet they don't need to be. Okay, you want them accurate and you want them fast, but you don't need them to be absolutely precise, because you're just after rough volumes of material type and what the spatial distribution of that material type is, and how do I go about sampling it. And you can then slice these models and start to see, oh, our quartz topaz, which is our zone with our highest grade tin, and for that matter, fluorite, is quite a large volume. The magnetite skarn is less, and the calc silicates are predominantly outboard. So we start to now understand our spatial distribution better, and we can design all sorts of test work based on that. The same data, when you count in also the spectral mineralogy, can be used to build quite good quality weathering models. In this instance, we weren't talking about sulfide transitional and fresh. We were talking about sulfide transitional and, sulfide zone, transitional, and a lot of supergene clay, including smectites. Okay, and there is tin up in this area as well, so, and copper. So there's an issue there that needs to be dealt with, but we can understand what that distribution is in terms of the model. Okay. So down to, well, now we've got our 3D mineralogical model. Okay. We understand what our distribution of minerals are. We understand what our weathering profile looks like. We understand what our precursor lithologies are, independent of the alteration mineralogy. And we know where our payable elements, in this case we're looking at tin, is distributed. But there's an issue, because some of the tin is in stannite, tin sulfide, not recoverable by gravity. And the client had no idea as to what proportion of the tin in their main high-grade ore zone was cassiterite versus stannite. Because we had both a fusion XRF analysis, which they'd done routinely for tin, as you do, and the 4-acid ICP-MS, where cassiterite's not that soluble, we were able to look at the ratio of soluble to insoluble tin and set their mind at ease to show that the blue zone in here, which was the main part of their high-grade zone, was in fact predominantly acid-insoluble cassiterite, and that the stannite is sitting outboard. Now, you'd expect that, but it's nice to have that confidence. The other issue that they had was this issue of being able to estimate from a resource perspective the amount of fluorite. They'd assayed fluorine, and they had assumed that all the fluorine was reporting to fluorite. The problem is that there was, when we looked at the fusion, at the fluorine estimate of fluorite on the y-axis here versus the stoichiometry of fluorite, i.e. the amount of fluorine and calcium, there was nowhere near enough calcium available to make fluorite from all of the available fluorine. So what this meant was that they had been overestimating the amount of fluorite in their resource. We were able to take that multi-element geochemistry and look at the maximum possible fluorite, in this instance close to this line here. Anything above that line is fluorite and carbonate and amphiboles, but down here, laser, this is excess fluorite that's reporting to topaz and salite. Excess fluorine, sorry, reporting to topaz and salite. So this is a critical thing. There was much less fluoride in this system than the client originally thought. But once we were able to break down this, we can say where are the zones where it's dominantly salite and topaz versus where is the dominantly fluorite, and allay that risk. So the takeaway message is you've got to characterise more, characterise earlier with good quality geological analysis methods, quantitative methods, and actually test, in terms of metallurgical test work, less. It's cheaper in the long run, it gives you more information early, and it enables you to demonstrate quantitatively why you should make the decisions you make at each decision point through the mining value chain. That client that I was just talking about with the fluorite project basically said at the end of this that it demonstrated that most of their preliminary MET test work, which was in excess of $250,000 worth of MET test work, was essentially wasted, and that they were going to go back and redo everything based on the outcomes of the geometallurgical model. So, in final summary, everyone should push for collecting the right data early in the project life cycle and think about how you're going to integrate those data with your geological logging, with your geophysics, with the geochemistry, spectral mineralogy, to build a live three-dimensional model that integrates the important data early on so your decisions are well-founded at the most expensive and highest risk end of the process. Thanks very much.